Okay, so first of all, I'd like to thank the organizers for inviting me to give this talk. And today I'll be discussing a measurement made with just a single black hole horizon. And this is the observation of quantum Hawking radiation and its entanglement in an analog black hole. And this is the world's first and only observation of spontaneous Hawking radiation in any system. So this work builds upon a rich theoretical history, starting with Jacob Bekenstein, who pointed out that a black hole should have both entropy and temperature. Then Stephen Hawking predicted that the black hole should radiate at the very temperature predicted by Bekenstein. And in making this prediction, Hawking combined general relativity with quantum field theory. This prediction is considered a first step towards achieving a theory of quantum gravity. Now, the difficulty in verifying Hawking's calculation is that the Hawking temperature should be exceedingly low. As we heard, for a black hole of a few solar masses, the Hawking temperature should be less than a microkelvin. But for smaller black holes, the Hawking temperature should be higher. So perhaps one could find a very small black hole, perhaps in the primordial black holes created in the early universe, might somehow be found, or maybe at the LHC, black holes might be created. And these small black holes, since the wavelength of the Hawking radiation is on the order of the diameter of the black hole, a smaller black hole has a higher Hawking temperature. In the meantime, Bill Unruh came up with the idea of an analog black hole, where sound plays the role of light. And in his paper in 1981, Bill Unruh wrote, "Black hole evaporation is one of the most surprising discoveries of the past 10 years. So apparently his motivation for inventing the analog black hole was to check Stephen Hawking's prediction. So there have been many systems proposed as possible analog black holes. Bose-Einstein condensates, superfluid helium-3, electromagnetic waveguides, ultracold fermions, rings of trapped ions, light in a nonlinear liquid, exciton-polariton condensates, and magnons in a magnetic wire. More recently, the entanglement has become of theoretical interest. Since Hawking radiation is pairs, as Ted explained in the previous talk, there's a particle which falls into the black hole and a partner which falls into the black hole, and the Hawking particle comes out of the black hole. So, and in a paper a couple years ago, a theoretical paper, I explained how one can easily measure the entanglement of the pairs, and I've implemented it here. So on the experimental side, my group has been studying this problem and only this problem since 2009, and we've made a systematic study developing all of the various techniques we needed to create analog black holes and to observe and create small numbers of phonons. And since the Hawking radiation is phonons in this system. Other experimental areas under study are surface waves in water. This is a classical system, and usually a white hole is studied. And the fluctuations in the water can stimulate pairs, or one can send waves which stimulate pairs. Nonlinear optical fibers are an active area of study, and the search for Hawking radiation is on in these systems, as well as exciton-polariton condensates. So now I'd like to mention how these analog gravity experiments relate to the information paradox. As Stephen Hawking proposed soon after predicting Hawking radiation, he explained that there should be an information paradox. So this is a real black hole, which looks a little bit, it's supposed to be a circle. And this is the event horizon of a real black hole. And the question is, what happens to information which falls into the black hole or is used to create the black hole? The Hawking radiation which is emitted should be random, and so it shouldn't have any information. So that's the information paradox. So there are many possible solutions to the information paradox that one can find in the literature. And one possible solution which one can find is that the outgoing Hawking radiation is entangled. Here's the Hawking radiation emitted at earlier times, and here's at later times. The entanglement between these two Hawking particles can contain the information. And this entanglement would be due to some effect of quantum gravity. So this solution to the information paradox has a difficulty, because the Hawking particle is already entangled with the partner particle inside the black hole. So this entanglement leaves very little entanglement left over for this entanglement coming out. And this is the very entanglement that we see, that I'll be discussing today. So the fact that we see this entanglement shows that there really is a problem of information loss, which makes difficulty for this solution to the problem of information loss. So, so in general, Hawking radiation, here's the black hole, as I mentioned. Here's a photon moving away from the black hole. It has positive frequency and positive energy, as similar to the photons all around us. However, this photon inside the black hole has negative frequency and negative energy. So one can then imagine a pair of these photons with zero total energy. And so these pairs can be created from nothing, spontaneously. Since they have zero energy, one doesn't need a source of energy to create these pairs. And so that's the Hawking radiation. And so there's a Hawking particle and the partner particle. And Hawking predicted a thermal distribution of these pairs. It's not just one frequency, it's a thermal distribution. So here's the analog black hole. This is a Bose-Einstein condensate. This is a 1D system, and the whitish region is high density. And over here, the grayish region is low density. So, and this Bose-Einstein condensate is flowing from left to right. So here, the flow is slow, it's subsonic, and here the flow is supersonic. So if we look at a phonon here on the supersonic side, which is directed against the flow in the co-moving frame with the fluid, due to the supersonic flow in the lab frame, it's falling back. It's unable to move forward and reach the analog of the horizon. So this is analogous to a photon inside of a black hole. And one can show that this phonon has such a big Doppler shift that the frequency is negative and the energy is negative. So, and now if we look at a phonon on this side, it can move forward against this subsonic flow, and it has positive frequency and positive energy. So again, we could have a pair of these phonons with zero total energy. And we would like for these pairs to be created by the vacuum fluctuations. So let's think about what the vacuum fluctuations are in a Bose-Einstein condensate. So here's a picture of a Bose-Einstein condensate with phonons. These lines here, this wave are phonons. So this is not vacuum, because when we say vacuum in this context, we're referring to phonon vacuum. And this image was taken in one of our works where we were working up to observing Hawking radiation, where we learned how to create and observe small numbers of phonons. Now here's a picture of a BEC with no phonons. So this is vacuum. And one can ask, well, where are the vacuum fluctuations? This BEC has some smooth macroscopic wave function. So where are the vacuum fluctuations? Well, if we look very closely at this BEC, we see that it's composed of point-like atoms, with basically an infinite density on top of one of the atoms and zero density in between the atoms. And there's a different configuration of these atoms for each realization of the experiment, and these are the vacuum fluctuations. And this is certainly true regardless of whether there are phonons in the BEC. So we're looking for the creation of these pairs, these Hawking pairs, caused by the quantum vacuum fluctuations. So how does one see these pairs? The Hawking radiation should be some very weak density fluctuations on top of this smooth background, and it should be some thermal distribution of these density fluctuations. It's been proposed in the literature that one can observe this by studying the correlation function. So we consider 2 points, x and x prime, one outside the black hole and x prime inside the black hole. And this horizon here should be emitting pairs in both the Hawking particle coming out and the partner falling in. So if one looks equal propagation times from the horizon, there should be correlations due to the pairs. And this is true if the points are close together or if the points are farther apart, the pair of points, as long as they're equal times from the horizon. So if we could plot x versus x prime, plot the correlation function in the x prime plane, and we see this band, this correlation feature. Each point along this band is a pair of points, x prime, which are equal propagation times from the horizon. So this band is how we observe the Hawking radiation. Now, to create the sonic black hole, we use a waterfall potential. So one can say that the condensate is flowing from the left, pours over this step potential, and gets accelerated to supersonic speeds. And how do we create this potential? It's created by this laser beam. So this is a laser beam coming out of this. It's a blue detuned laser beam relative to the atomic resonance, which implies that it's a repulsive potential. The atoms feel this laser beam creates a repulsive potential. So this is an elliptical shaped laser beam coming out at us, and it's been cut in half by a knife edge and then imaged onto the condensate. So there's a steep transition from the light to the dark, and that creates this potential drop. Now and then this laser beam is moved at a constant speed to the left. It's useful to consider the reference frame where the laser beam is stationary, meaning the horizon is stationary, and the condensate is flowing from left to right. So then in that reference frame, the condensate is coming from the left, it's moving right, pours over the potential, and gets accelerated to supersonic speeds. So in addition to this laser beam, we need to image the condensate. So there's another laser beam coming from below, and it's imaged by this, the condensate is imaged by this high-resolution optics. And the condensate, due to its index of refraction, puts a phase shift on this beam, and that's what's imaged. Furthermore, there's another laser beam coming from here, which traps the atoms into this tube-like volume. This is a red detuned laser beam, so it attracts the atoms into this volume. And however, we would like low density because it enhances the signal of the Hawking radiation. So this laser beam, to create the low density, this laser beam must be very weak. It's much too weak to support the atoms against gravity. It can only support the atoms, cancel about 10% of gravity. So there's a magnetic field gradient which cancels gravity. So here are some experimental numbers. Here on outside the black hole, the speed of sound is 0.57 millimeters per second, and the flow velocity is 0.24 millimeters per second. So this is subsonic flow. Over here, inside the black hole, the speed of sound is 0.25 millimeters per second, and the flow velocity is 1.02 millimeters per second. So it's very much supersonic on this side. And we can see that this is a 1D system, since the trap frequency, confining the atoms in the radial direction, is 140 hertz, whereas the typical interaction energy of the condensate is 70 hertz. So the radial degree of freedom is frozen out. Furthermore, we can show that, that this system is phase coherent over a length scale much longer than the length of the system, even though it has been predicted that even if the system were not phase coherent, one could still see Hawking radiation. Now, this is an integrated profile of this density profile. Of the density. What we're seeing here is the density integrated in one dimension to make this two-dimensional plot. So here is an integrated profile, and this blue region is where we're going to see the Hawking radiation, and the red region is where we'll see the partner particles of the Hawking radiation. And so if we zoom in on this horizon region, it looks like this, and we can see the width is a few healing lengths. The healing length is sort of the minimum length scale of the condensate, maybe similar to like a Planck length scale, you could say. So it's a few healing lengths in width, the horizon region, implying that it's basically a hydrodynamic flow. Furthermore, it agrees with the green line. The shape is approximately in rough agreement with the green line, and this is the theoretically predicted shape, which is referred to as half a gray soliton in the language of Bose-Einstein condensates. So we're going to consider actually two different types of experiments. In the main experiment, the Hawking radiation experiment, we move the horizon, the potential creating the horizon, at a constant speed. And this is as I described earlier. But we'll also look at a preliminary experiment where, in addition to the horizon moving, it's caused to oscillate. So here, as a function of time, there's this constant motion plus this oscillation indicated by the green line. So the horizon oscillates, and the horizon acts like a sort of a piston, creating waves traveling out of the black hole and into the black hole. And so by looking at these outgoing waves, we can see what the outgoing waves of the system are and see what waves would we expect, outgoing waves would we expect in our Hawking radiation. So first, let's look at this preliminary experiment. So here's the correlation function in this preliminary experiment where we choose a certain frequency and cause the horizon to oscillate. And you could see in this quadrant, this is the quadrant which is correlations between inside and outside the black hole. You could see this wave pattern. So these are just the correlations between the positive energy waves outside the black hole and the negative energy waves inside the black hole. And by taking the Fourier transform, just looking at the wavelength of this picture, we can get K, we can get the wave number, and trace out the dispersion relation, apply different frequencies, and measure the resulting wave number. So here's the dispersion relation outside the black hole. These waves are moving, since the group velocity is negative here, it's sloping down to the left. It implies that the wave is moving to the left, so it's moving out of the black hole. Here, inside the black hole, here's the dispersion relation. These filled circles are the negative energy modes, and they have a dispersion relation implying that they're moving to the right, so they're trapped inside the black hole. However, we see due to the nonlinear dispersion relation of the Bose-Einstein condensate, this curve rolls over, so there's some maximum K and maximum frequency which is trapped inside the black hole. These waves over here are not trapped. They can move towards the horizon. So there's some maximum K which we expect in this Hawking radiation, and this maximum K which we observe in the preliminary experiment closely matches the maximum K which we'll see in the spontaneous Hawking radiation. Another thing which we can see is study the rate at which these phonons are created, at which the waves are created for each frequency, because it's the same horizon here producing the waves regardless of whether it's in this stimulated experiment or in the spontaneous Hawking experiment. So there should be some similarity in the frequency response that the horizon has, what wavelengths it can produce and which frequencies. So these filled circles shows as a function of frequency the rate at which the waves are produced in the preliminary experiment, and the dashed curve is what one would predict given the measured Hawking temperature that we're going to see in the spontaneous experiment. And so within an overall constant, the two curves agree well. Another thing which we could look at is the angle of this feature. The angle of this feature in the x prime plane. It gives the ratio of the phase velocities inside and outside the black hole. And the angle of this feature also agrees well with the angle seen in the Hawking radiation experiment. So now, let's move on to the main experiment, the Hawking radiation experiment, where we no longer cause the horizon to oscillate. We just move the potential at a constant speed. And we get this correlation function. And so we can see this band starting at the horizon and traveling out. These are the correlations between Hawking and partner particles. So this is the observation of the Hawking radiation. And this correlation function was obtained by an ensemble of 4,600 repetitions of the experiment corresponding to 6 days of continuous measurement. So one thing we can notice about this feature, is that it has a profile it has some finite profile. So here's the profile of it, obtained by integrating along lines parallel to the feature. So here's its profile, and it's sort of similar to a Gaussian. And so this finite area that it has, one can show that that implies a broad K distribution. It implies a thermal distribution, that the population goes like 1 over omega for small omega. So we can compare with simulation. So here's a simulation, and it looks numerical simulation. It looks similar to the experiment. And the profile also looks similar. But in the simulation has these bands. These are an artifact due to the way that we introduced the fluctuations into the simulation. And these fluctuations are introduced into the simulation well after the creation of the horizon. So this shows that this Hawking radiation is a stationary effect. It's not related to the creation of the horizon, the time-dependent creation of the horizon. So we can also extract the population of the Hawking radiation. So we look in this blue region, and we compute the power spectrum of the fluctuations in this region. And this is using a technique which we developed working up to observing Hawking radiation. So this power spectrum of fluctuations is proportional to the population plus 1, where these are the quantum fluctuations. So we can extract this population. So here's the power spectrum which we measure, the solid curve. And the first thing that one might notice about this power spectrum is that it slopes downward from right to left. And this is a sign of quantum fluctuations, since a thermal spectrum, as you go to lower energy, has more and more fluctuations, like a Planck distribution. And so here, this zero curve is the pure quantum fluctuations. And the difference between the measurement and the zero curve gives the population. So here's the population which is extracted. And it fits well with this Planck distribution indicated by the dashed curve. And the extracted temperature is 0.36 mc squared, where c is the speed of sound, or 1.2 nanokelvin. So that's our measured Hawking temperature. Now, I'd now like to explain how we measure the entanglement. So using this very same correlation function, this is a position space observation of the correlations. We can simply take the Fourier transform of this picture and get a momentum space observation of the correlations. And that corresponds to this product of operators here. So this ensemble average. This is an annihilation operator for a Hawking particle, and this is annihilation operator for a partner particle. So by taking the Fourier transform of this profile, of this correlation feature along the x double prime direction, we get this product of operators. Once we have this, we can plug into this criterion, non-separability criterion, which one can find in the literature, which shows that if these correlations are stronger than the populations, then this delta becomes negative, and one has, and this corresponds to non-separability or entanglement. So in other words, if the correlations are strong enough, seen here, then implies entanglement. So in deriving this expression, an approximation has been made. We've neglected these three terms in order to get this term. These three terms are all correlations between different k's. For example, a positive k and a negative k. We can see that these waves have different frequencies. So here, if we look, here's a positive k, and here's a positive k partner particle. These have the same frequencies. However, this wave with negative k, due to the Doppler shift, since this is a flowing condensate, this wave with negative k has a different frequency from this k, so it has a different frequency from the partner. So these are all, each of these terms is correlations between waves of different frequency. And it's difficult to think in this system what would cause correlations between waves of different frequencies. So Hawking radiation certainly wouldn't. And so we can safely neglect these terms. In fact, in a recent theoretical paper, it's been shown that, that in a stationary system, then they vanish exactly, these correlations between waves of different frequencies. So in other words, this method of measuring entanglement is not a general method for measuring entanglement in a system. We've taken advantage of the type of system that it's an inhomogeneous flowing condensate. Furthermore, one might like to measure non-commuting observables to measure entanglement. So we can see that these correlations don't commute with the populations. So these are the non-commuting observables, although it's been recently been shown that one can measure entanglement even without non-commuting observables. So we might want to check, we can check that this method of measuring entanglement works in a case that we know well, which is the hydrodynamic approximation, which is in strict analogy with a real black hole. So in this case, let's first apply the technique. We have the correlation function, which is calculated in the hydrodynamic approximation. We take the profile of it along the x double prime direction. Then we take the Fourier transform squared, and we get this solid curve. We then can compare it with the populations, and here's the populations, the dashed curve. We see that the correlations, for every frequency, the correlations are above the populations. So this mean implies entanglement at all frequencies in this hydrodynamic approximation. Now let's see what we would predict from the usual calculation of Hawking radiation. So here we have the Bogoliubov transformation for the Hawking particles and the partner particles, where beta here that appears, beta squared is given by the Planck distribution, and alpha squared is beta squared plus 1. We can plug this Bogoliubov transformation into this expression, and we immediately find that it's given by alpha squared beta squared. This curve here is exactly alpha squared beta squared. So our technique worked of taking the Fourier transform of the correlation function gives us exactly alpha squared beta squared as we would expect. Furthermore, the strength of these correlations, are limited by the Heisenberg uncertainty principle. They can't be greater than beta squared plus 1 beta squared. And so you can see where alpha squared beta squared is beta squared plus 1 beta squared. So we're exactly at the Heisenberg limit. So this implies that we have maximal entanglement at all frequencies in the sense that it's limited by the Heisenberg uncertainty principle. So let's apply this to the experiment. Here's the profile of this correlation feature. We want to take its Fourier transform squared. So here's its Fourier transform squared. And here's the measured population, the dashed curve. And we see that the solid curve is above the dashed curve for a broad range of k's. So this corresponds to the entanglement, every place where the solid curve is above the dashed curve. And here we can take the difference between the solid curve and the dashed curve as shown here. And so this is minus delta here. And so any place where this is positive corresponds to entanglement. We also see that these correlations end exactly here at k max. K max was the maximum k seen in the preliminary experiment. So we see the correlations end where we would expect that they would. Furthermore, we can see that there's this light gray curve. This is the Heisenberg limit. And we can see that the agreement between the correlations and this Heisenberg limit for the highest k's, implying we have approximately maximal entanglement here at the very highest k's. But then as k drops down, we're much lower than the gray curve. So we have much less than maximal entanglement. Furthermore, the agreement here with the Heisenberg limit implies, since the Heisenberg limit was computed by a Planck distribution, the agreement here implies approximately a thermal distribution up here at the highest k's. And here's the numerical simulation which qualitatively agrees with the measurement. So we can make a statistical analysis for how robust is this observation of entanglement. So we could consider two possibilities. One, perhaps this measured population is really much warmer. It's really way over here at 2.7 nanokelvin, in which case the population would no longer be below these correlations. However, if we look at the measured power spectrum, we see that the 2.7 nanokelvin is ruled out by the measurement by many sigma. Another case we could consider is perhaps these correlations, this spectrum of correlations, is actually much narrower due to noise. So that would imply, since this is the Fourier transform of this band, it would imply that this band is actually much wider. It appears to be, to the eye, to be narrow, but maybe it's actually much wider. So here's the profile of this band. With the statistical error bars on the band, it's, the width is determined plus or minus 16%, but it would need to be wider by 90% in order to bring this curve all the way over to here. So the entanglement is confirmed with a significance of 5.7 standard deviations. So in conclusion, quantum Hawking radiation is observed. The Hawking radiation is observed through the correlations between the Hawking and partner particles. The quantum nature of the Hawking radiation is verified by observing the entanglement between the pairs. And the experiment is well within the quantum regime characterized by entanglement and spontaneous emission, since the 1.2 nanokelvin measured Hawking temperature is much less than the 2.7 nanokelvin limit, which we saw. The measurement shows maximal entanglement at the highest energies and no entanglement at the lowest energies. Thermal behavior was seen at the very low energies as well as at the very high energies. The preliminary experiment verifies the Hawking temperature by the rate at which the particles are created in the preliminary experiment. It also verifies the ratio of the Hawking partner phase velocities due to the angle of the correlation feature in the XX prime plane. And it also verifies the width of the Hawking partner correlation feature by means of that maximum K. Both experiments had the same maximum K. The simulation verifies the approximately stationary background on which the Hawking radiation occurs, as well as the width of the Hawking partner correlation feature by that maximum K. So what are the implications here for real gravity? What have we learned about real black holes by this measurement? Firstly, we've learned that black hole thermodynamics is verified experimentally, at least in the analog sense, since an analog black hole does radiate, and this confirms Hawking's calculation. The Hawking partner pairs are entangled. We're seen to be entangled, and this confirms an important element in this discussion of information loss, because as I mentioned earlier, it limits the outgoing information available. Thank you.
I'm sure you've been asked this question before, but how do you know in the case where you're looking for the spontaneous emission and you're moving the horizon along, that it isn't, weakly fluctuating a bit like what you were doing in the stimulated emission case? How do you know that you're driving it sufficiently smoothly that you're not actually stimulating emission?
I see. Well,
potential movement.
The stimulated emission would not be entangled. So that's how you know that it's spontaneous.
Okay.
Hi, thanks for the talk. I don't want to take anything away from the amazing experiment, and it's a real tour de force.
Thanks.
I'd just like to say that from the point of view of somebody who's thought about information loss, thanks to Stephen, I don't understand how we can possibly hope to learn anything about that problem from this type of experiment, because the question wasn't really whether Stephen made a mistake in his calculation. The question is which equations describe the system correctly. So it seems to me that this tests that non-relativistic quantum field theory describes this condensed matter system correctly. If it does, this had to work. The only thing you could have discovered is that that's not true, which would have been extremely surprising given that we've already applied that theory to those systems extensively. But there's a key element that's missing in the analog black holes, which is that they don't evaporate, they don't disappear. The information loss problem is so severe because we're at the end left with no black hole at all and just the Hawking radiation. That's as if whatever's on the downside of the waterfall somehow disappears, and the information that's there has to get over the waterfall to the other end. And there's just no analog of that question we can even ask.
Yeah, this analog black hole has no information paradox itself. The only thing which we observe is the entanglement, which is often assumed in discussions of the information paradox. As I mentioned, when Bill Unruh invented the idea of an analog black hole, he said black hole evaporation is one of the most surprising discoveries of the past 10 years. So now, more than 40 years later, maybe we say, oh, of course the semi-classical calculation is correct. That was not the case 40 years ago, and it's taken this long in order to make the verification.
So I guess in this case, you're just measuring commuting observables, and then you're making some assumptions to kind of infer what would happen if you measured non-commuting observables. And then you said something like, but it can be shown that if I measure just commuting observables, I can still show that there's entanglement.
Yes.
If I'm only measuring commuting things, then for all I know, someone has come and measured my system beforehand, and there's no entanglement whatsoever. So how, I guess, in the case that you're presented now, how sure are you that you can infer correctly what you would measure if you measured the non-commuting observables? And then maybe you could explain the other statement you made, which to me was quite puzzling.
Yes, okay. So, first of all, that one sentence that I threw out quickly, that one can make a measurement with non-commuting observable, measure entanglement by non-commuting observables. This is in Renaud Parentani's paper, and he's discussing a different system. He's not discussing, so I was just saying in principle, one does not, okay, but that's something not related to this exactly, making the measurement with non-commuting observables. For this system, as I make the measurement by using commuting observables plus the assumption. And the assumption is I say that there's no correlations between waves of different frequency. So yes, there is an assumption. How sure am I of that? So the only question is, how sure am I of my assumption? And I could certainly not think of any mechanism that would do such a thing in my Bose-Einstein condensate. And furthermore, there is a proof that if the system were perfectly stationary, then they would identically vanish. That's another piece of evidence. So those are what I base my assumption on.
If there are no further questions, let's thank the speaker again. Do you want to give... What?